Yeah, let's look at the terminal characteristics of diodes. So we know that it's only conductive in one direction. So it's being used for some special applications. So for example, rectifiers, from AC to DC. But before we're not going to design any rectifiers in this class, but we still have to look at the terminal characteristics of the diodes. See how that works. Okay. So this comes from the PN junction and the diffusion layer as well. Since we know that this carries more free holes, this carries more free electrons, so there's a concentration gradient, so the holes will diffuse to the right hand side and the electrons will diffuse to the left hand side to neutralize the holes, and the holes will neutralize the electrons and also has more left after that neutralization. So that's why this depletion region, so both of these two regions are depletion regions, but this part, the right part half, is positively charged and this is negatively charged. So it forms an electric field. And that electric field gives you a VB. It's called a built-in potential, built-in voltage or built-in potential, or it's called barrier voltage. And usually in silicon, VB is from 0.6 to 0.9 volts, and we'll usually just use 0.7 volts. So which means there's a 0.7 volts. Now you have to invert it in order to get the current flow from the P to N. If you connect a battery to the diode, it has to be larger than 0.7 volts in order to get a current flow in that direction. Why? Because the electric field is applying a force in the other direction, so you have to overcome it first. All right. In that case, this diode is going to have a 0.7 voltage drop after you apply a voltage. This can be confusing because 0.7 volts is in the middle. Right now we are looking at the built-in potential. It's from right to left, is plus minus. But now, if you have a battery, definitely a resistor to limit the current, okay? If you forward bias the diode, it has to, so whenever you are increasing the voltage of the battery, for example, if you can do that, okay, you're trying to increase the voltage from 0, and whenever it is 0.4 volts, there's pretty much no current. Let's consider there's no current flow in there. Until 0.7, it reaches 0.7, you are getting a significant amount of current flow through that PN junction. And there will be a 0.7 volts drop from P to N. That can be confusing, right? Because we are looking at here is from right to left. But now we are talking about there will be a potential drop from left to right. It's going to be there. Whenever you get this diode to conduct current, whenever this voltage is larger than 0.7 volts, and there will be a 0.7 volts drop across the diode because it has been using that voltage to invert that one in order to get a current flow through the PN junction. All right. So in that case, if I have a 5 volts here for the battery, and so what's the voltage will be dropped across the resistor? And this won't increase. If it has a 0.7 volts VB, it's going to be 0.7 volts drop from left to right, always, whenever the power supply is larger than that. So if this power supply is only 0.5 volts, can you have a 0.7 volts drop from left to right? No, only when you have a current flow. Okay, so if you have a 0.7 drop here, then what's the voltage dropped across the resistor? 4.3 volts, right? If it's 7 volts, what's the voltage drop here? 6.3 volts. Get that? Okay. So now let's look at some examples. So for this voltage, that's a DC voltage. That's a resistor. So this is a real diode. It's a real diode. So what does an ideal diode looks like? That's an ideal diode, right? So for a real diode, 0.7. Okay, threshold voltage. If I increase V, so just please plot the voltage, the input and output voltage. No, the input actually the x-axis. So it's going to be VI here. So plot VO, if this is grounded. Plot VO when V in was originally negative and then becomes positive because here's 0, here's the origin. And if V increase linearly like that, what VO looks like. So first, when VI is negative, what's going to happen? When VI is negative, so when VI is negative, which means the potential here is higher than here, so there won't be any current flow through the diode. So whatever voltage applied to here will be the same voltage here as well, because there's even no current flow. Look at this network, it's all disconnected. You got a resistor, but there's no current flow through it, so this resistor is not going to drop any voltage. So VI here, VI here. So what that looks like? Huh? No. VI is going to change like this linearly. So think about that. I'm providing a DC sweep to VI. So the VI is changing from here, from negative to positive. And VO will be the same as VI. So that's exactly Y equals to X, right? So what does that function look like? Is that flat? No, it's not. Oh, no, it's right. Boom. Is that correct? Okay, because why is that? Because X equals to Y, right? X equals to Y. They are both negative. What about after that? Say it again. Yeah, until the threshold voltage. Then what? This becomes conductive like a wire. It's going to short these two terminals. And there will be a permanent 0.7 volts drop. So what VO looks like? What is VO? VO will be permanently 0.7 because this is two terminals across the diode. The diode is like a battery or a voltage source, right? It's constantly dropping to 0.7. That's why you need a resistor to block these two, right? If you short these two, then what VI is, VO will be the same voltage. But you got a resistor. Okay. So that's example 1. Let's look at example 2. What about this one? So when Vi is negative, this will conduct voltage or current. Because here's higher, here's lower. Until when? Yeah, negative 0.7 volts. It'll be like this. And this. So this is negative 0.7 volts. What about this one? So whenever Vi is smaller than 0.7, larger than negative 0.7, it should be linear. Because neither of these two diodes will be conductive, right? So we like this only within this region, this range. But after that, it's going to be flat. So this is negative 0.7 volts, and this is 0.7 volts. That's a 5 volts battery. I can tell plus minus from top to bottom. Vi, Vo. So let's assume there's current flows through it. Then there will be a 0.7 volts drop from top to bottom. And because whenever you are getting two batteries stacked together or put them in series, it's usually from plus minus, right, in that direction. You have two batteries, right? You're going to put them in series, it looks like this, plus minus, so you can get the voltages being added together. If this is 1.5, so overall you got 3 volts. So you got plus minus. So overall here, you have 5.7 volts to overcome or to invert. So whenever you plot this Vi, Vo, whenever this Vin is lower than 5.7, it should be linear. Whenever it reaches 5.7, the current is going to flow in that direction, like this. Sorry. Zener Diode. So remember the IV curve for the Zener Diode? It is able to stabilize the voltage at VZ whenever this is being reverse biased. So we can have the voltage here to be stabilized at like the 30 volts or other voltages you can select from the vendor, right? For example, it's 3 volts, it's going to stabilize the voltage at 3 volts. So the voltage here, VZ, will be 3 volts, and the voltage here will be negative 3 volts. It's also a silicon material, so it has a 0.7 volts built-in voltage, built-in potential. Whenever it's forward biased, it's been forward biased, also has that 0.7 volts. So if you have something connected like that, whenever here you get a 0.7 volts drop, and this reverse biased Zener Diode is able to stabilize the voltage at something, for example, VZ, plus minus. So the curve looks like, what's the voltage here? And what's the voltage here? So what are these two? Let's just use VZ for now. So here will be 0.7 plus VZ, right? Is that correct? So what is this? It will be negative 0.7 plus VZ. Electrostatic diode protection circuit. During the winter, whenever it becomes very dry, low humidity, then there are a lot of electrostatic shocks you can feel, right? Whenever you switch on the light. So these voltages are usually thousands of volts. The current is low, so that's why you are still safe. Sometimes goes to tens of thousands of volts, like 20k volts. It just happened in less than like maybe just 10 milliseconds or something. So, and the current is low, power is low, so it couldn't feel that much. But the thing is, the chips, all the transistors are very sensitive to voltages. So if I give you a 5 volts semiconductor material like a Arduino chip, if your finger has that 5,000 volts static shock voltage charges on your finger, you touch that microcontroller chip, it's going to blow it up. So that's why usually for the standard operation, you have to wear that little ring here and then short it to the ground. So it's going to discharge all the charges from your finger when you touch these microcontrollers or integrated circuits. And usually we don't do that in the lab. You can see like there are so many people and they'll walk around in a lab, grab a chip, just plug into the breadboard. Usually it's fine, but sometimes probably you shouldn't break any chips. If you don't wear that one, maybe you grab 10 chips, you can break one. So it's not like breaking 9. So usually we don't wear that grounding ring. But in the IC design, you can design these ESD diodes protection for each pin of the chip. So for example, the chip has many pins. Usually we have that ESD diode right after that pin inside the chip to protect it. So how that works? If you got a 20 volts, for example, 20 volts power supply for everything here, and that's the input. That's a resistor. So everything is powered up at 20 volts. Okay, so 20 volts is very close to the maximum voltage the chip can handle. If this voltage here, the input voltage has 2000 volts at some moment, if you have this circuit to protect the chip, So what's the voltage here will be? You have 2000 volts. So this will drop 0.7 volts plus minus, right? And what's the next? So this power supply is a power supply and grounded, right? So that power supply must have some sort of protection inside. And it's a voltage source, which means it's going to supply 20 volts forever, as long as it works, it's functioning. So the voltage drop between these two nodes will be permanently 20 volts. And you get a plus minus here, which is 0.7 volts. So what's the maximum voltage can appear here if you have 2000 volts? Doesn't matter, 30,000 volts. As long as it's not being blown up, right? So what's the voltage here will be? 20.7. Maximum. Okay? So what about the negative voltage? I mean, no matter it is plus 20,000 volts or negative 20,000 volts, they're all damaging, right? Because voltages are relative. It doesn't matter, like negative 20,000 volts is a low voltage. It's not. It's a pretty high voltage. Yeah, it's going to do the voltage drop and run a lot of current through it. So what about the negative? If there's a negative 2000 volts, what's going to happen? It's pretty high. It's going to damage the chip. But the thing is, you got a 0 here. If you got a negative voltage here, then this becomes conductive, and it's going to drop a constant 0.7 volts across it, right? So no matter what voltage it is at the input, it won't increase anymore because it's going to run a lot of current to drop that voltage across the diode. They probably need a little resistor. But the thing is, because this 0.7 volts will be the constant voltage across the diode, so the voltage here won't be negative 2000 volts, right? So what's the voltage here would be? Huh? Yeah, it's negative 0.7 volts, right? Is it? Because here's 0 volts, and you got a 0.7 volts drop, so 0 minus 0.7 will be negative 0.7. You are thinking about like 2000 volts, negative 2000 volts being added to here. Why this diode can run all the current and drop the voltage? It's actually pull the voltage down to the ground, very close. But whenever it reaches negative 0.7, it just stops. So why it is able to do that? Because that one, the 2000 volts is not a voltage source, right? It's not a voltage source. It doesn't like this one. It can it's being plugged into the outlet. It's being supplied by the power plant. It is able to supply whatever current you need. This is not. You are not a power plant. It just has some charges. It's a pretty high voltage, but the current is very low. Whenever you discharge it, the voltage is going to decrease like crazy. So that's why it is able to be discharged really quickly. Okay. Example 7.
circuit.
Hmm?
That was a positive and then try the chip, right?
If the positive 20K is going to make this diode conductive because this is higher than 20 volts, higher than 20.7 volts. It's going to discharge through here really quickly. And then stabilize that at 20.7. Yeah, the power supply is grounded, right? So there's a path for the charges to flow. Actually, it goes to the ground. You know, the last example for diodes, then we're done for diodes. No worries, I'm not a Superman. You guys are tired, I'm tired too. All right. So, how can I get started? There are some different conditions, right? If you look at the polarity of the diodes, no matter what, whenever you got a positive voltage here, no current is going to flow because this diode, because of this diode. And so if VI is larger than 5 volts, definitely still nothing here, so the circuit becomes this. Only this one exists because only this one conducts current. This one is being blocked. So what is VO? $10K. So how to do the calculation? Ideal diodes. No reverse breakdown. To make your life easier. So VI plus minus. So if you start from VI, like a little person start walking in a loop, you can get a KVL. So the first sign here is negative, so it's negative VI plus 10K ohms times the current plus ideal diode, so no VB, plus 5 volts plus 10K times I equals to 0. Since we want to calculate for VO, and VO equals to 5 volts plus 10K times I. So I, if you calculate I from here, it is VI minus 5 over 20K ohms. And plug into here, you're getting VO equals to 5 volts plus 10K times and this equals to 2.5 plus 2.5 volts, but plus VI over 2. Since we don't know what is VI, so this is a function of VI. VO is a function of VI. And if VI is smaller than negative 5 volts, so it's negative right now, which means potential here, voltage here is higher than here. So possibly it can run the current in that direction from bottom to up. But this one will be blocked. No matter what, it's going to be blocked. Is that true? Right? No matter what, because the potential here is higher. There's no way you can run current in that direction. For this one, it's possible if you can overcome that 5 volts. If it's larger than that 5 volts. So which means if this is larger than 5 volts, this will be smaller than negative 5 volts, right? So that's why we got this, and the circuit becomes so negative VI plus 10K times I let's assume the current flow in that direction. It'll be minus 5 volts and plus 10K. VO equals to negative current flow in that direction. So VO equals to 5 volts plus 10K times 9. I know current is not flowing in that direction. I can assume that current flows in that direction, right? So I can do the calculation. There will be a negative sign afterwards. So I equals to VI plus 5 over 20K. This is I, like that, that's I. So VO equals to negative 5 plus VI plus 5 over 2. Is that right? Which is VI over 2 minus 2.5. I'll calculate it. Any questions on this? No? All right. There's one last condition for this one, which is when VI, so if VI is larger than negative 5 volts and smaller than 5 volts, so there's no current flow through the circuit, right? Nothing is going to flow through anywhere. So VO will be exactly VI because there's no current. So what voltage appears here will be transferred to VO as well. So VO will be exactly VI. The circuit looks like this. VI, 10K, VO. So current is going to flow through either of these two diodes. Okay. Done for diodes. I'm going to give an introduction to BJTs because you'll be able to see BJTs in a lot of places. It can be frustrating if you do not know what's going on for that device. It used to be everywhere even for digital circuits in the past because it consumes way more power compared to CMOS transistors. So we do not use that for digital circuit anymore. But still for analog or power supply circuits because it is able to handle more current compared to CMOS transistors. So in the past, before the MOSFETs were invented, transistors means BJTs actually. Bipolar junction. So the symbol is like this. It's called NPN. Or this is a PNP. So this terminal is not a drain, right? In CMOS, NMOS, this is called drain. It's called source. This is called gate. For BJT, for NPN, this is called collector. This is called emitter. This is called base. So in NMOS, current flows in that direction. In BJTs, current flows in that direction as well. They both behave like a switch. You have to turn it on to allow the current flow through it. But for this one, between the gate and the channel, there's a dielectric material. It's a silicon dioxide. So there won't be any current, DC current flows through that, static DC current flows through that transistor to keep it on. So it's controlled by the voltage. So this is a voltage controlled current source. Because whenever voltage reaches a certain level, it's an IV curve. For the NMOS, the current ideally won't change anymore. It's like a current supplying current after that certain voltage. So it's a voltage controlled current source. If you got different VGS, you can have different current output for the NMOS. For this one, it's different. NPN means there are three junctions or three pieces of semiconductors. It's N-type, P-type, and N-type. Put them together. If you only have a PN junction, it's a diode. If an NPN is a transistor. So that's a base. They must have a metal here to make the better conduction. Here as well. Here as well. So that's C, that's B, that's E. That's why for some of the chips you have been using, it has a part. For example, here's a chip. You can see the power supply and ground usually being laid out like that. That's the IC chip, okay? And sometimes the pin's name for the power supply is called VCC, right? But sometimes it's called VDD. What's the difference? So VCC is the circuit must be built based on the BJTs, and usually we part up the collector of the BJTs. That's why it's called have a C here. But for the VDDs, they are MOSFET based power supply or transistors. It's usually being part up at the drain. That's a D here. That's why sometimes the VCC, sometimes VDD, but they are both the power supply for the chip. So here's the BJT transistor, and there's no silicon dioxide in between the wire, the metal, and the semiconductor piece here. So which means the DC current is going to run through it constantly, right? If you have an NMOS, you part it up, all right? You part it up. There's only a voltage, a static voltage here to invert that channel to open up the channel. So if you give a pressure here, it's going to run the current flow through the channel. So it consumes less power because there's no current that runs through it when you're trying to turn it on. But this one is different. If you give a voltage, the current is going to flow. It's a diode here, right? It's going to flow. You have a static current constantly flowing in the base. Even though it's small, but still it consumes more power. So how that works? How this can be used as a switch? And we have covered that in logic, but we'll cover more about it later regarding the mechanism of the function of this of the MOSFETs. But for this one, we all know that if you have higher potential here, lower potential here, this PN junction is being what? Biased. No, I mean, what type of biasing? If you have higher potential here, lower potential here, is being forward biased. So there will be a current flow through and there will be a 0.7 volts drop, right? Okay, it's gonna conduct the current through it. If you get another potential here, so this little current will induce a larger current flow through the transistor from the collector to the emitter, and that current is called IC. And that behavior is dominated by, conclusion from physics. So IC equals to IS times E to the power of VBE over VT. So VBE is the voltage potential difference, the voltage difference between these two terminals. Constant. And you can get a collector's current from the top to the bottom. So IC is usually beta times larger than IB. There's an IB here. And IE equals to alpha times IC. So that's the gain of the BJT, and it's usually 100, 50, can be 200. So that's the current gain of the transistor. That's why you can get a current amplification. That's why I want to use it, right? You give a little current here, then it's being amplified by 100 times. So you can connect these two terminals and turn it on, turn the channel on. You can flow current through it. This is usually like 0.9 or something. in that level. And since we can see that IB is flowing into the base junction, and IC is flowing from top to bottom, and they will merge at the bottom and form IE. So IE equals to IC plus IB. So IE, because IB and IC merge together to form that IE. So IE equals to IC plus IB. And from these two, we know that IE equals to 1 over alpha IC from here. So based on this equation, we can get 1 over alpha IC, which is IE equals to IC plus IB. So IB will be IC over beta. So in that case, IC can be cancelled. So we're getting 1 over alpha equals to 1 plus 1 over beta, which is beta plus 1 over beta. Right, so alpha equals to beta over 1 plus beta. Still from here, if you move 1 to the left, it's alpha, 1 over alpha minus 1 equals to 1 over beta. So beta equals to 1 over alpha minus 1, which is alpha over 1 minus alpha. All right, so that's the conclusion here for the BJTs, and I think these are the most equations you need to know. This pretty much covers everything I need to cover for this class. You'll learn more details about them, AC, whenever you get an AC signal, what are the AC gains, all these kind of details. It's going to cover probably, I think it takes a month or so, like 4 weeks, 5 weeks to cover everything about BJTs. The conclusion, so after the calculations, the conclusion here, first, IC equals to beta times IB. That's the main reason why we want to use BJTs, because amplifying the little current being injected into IB and amplify it by beta times, and beta is usually 50, 100, 200 times. First one you need to know, and the most important one you need to know about the BJTs. Okay, IC equals to beta times IB. Second, IE equals to IB plus IC. Third, alpha equals to beta over 1 plus beta, and beta equals to alpha over 1 minus alpha. And that's it. For now, you need to know. And works, there are several different modes that you can operate that BJT. Because the IV curve looks like this. If this is VCE, if this is IC, it looks very similar to the MOSFETs. So these are different VBEs. Okay, and there are several regions. So this is called cutoff region. And this is called saturation region. It's different from MOSFET. and this is called active region. And we usually operate the BJT in the active region. And you can see that it's not flat. And if you draw that curve and get an intersection with the x-axis, this is called VA. This is called early effect. Because to operate that BJT, be in the active region, VC must be larger than VB. So VC larger than VB, larger than VE. That's a requirement to operate that BJT in here. So which means this voltage has to be the largest. It has to be the largest, then the second largest, then the smallest. Okay, so you can push the current flow in the channel. And so here's a question. If I have VC larger than VB larger than VE, this definitely, because this is larger than this, so I know that the pin junction from B to E, that little pin junction here is being forward biased. So there will be a current flow through it, no problem, right? And from here to here, because the voltage is pretty large, so it is able to push that current or the charges to tunnel through these depletion regions. So that's how that works. But now, before we just understand, okay, so the charges will tunnel through that, all these layers of depletion regions and make that happen. But if you are only looking at this pin junction here, it's NP, right? It's NP. And the voltage at N is larger than the voltage at P. So how this is being biased? Reverse biased. Okay, it's being reverse biased. So whenever I increase VC, like when I increase VC, what's happening for this pin junction here? For the depletion region, is it getting larger or smaller? If I increase the voltage, the reverse biasing voltage. Is this depletion region getting wider or smaller? How to remember that? Remember from last time I told you? Becomes larger, right? Because whenever you forward bias a pin junction, it's actually pushing that depletion region to become thinner. Whenever it's thin enough, the charges can directly tunnel through it to make it conductive. But now here it's getting larger. So whenever this is getting larger, it's going to push the base layer to be thinner. Right? So it's getting a larger current because the base becomes thinner. So it's easier to run through that thin layer here. It's getting thinner, 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 thinner. So we got more current. So that's why it's not flat. Whenever C is larger, so current is going up. And you can get an intersection between that curve and also the x-axis, and that voltage is called early effect. It's called VA. It happens to the MOSFETs as well, and we're going to cover that in the future. Okay. All right, that's everything for today. We'll do the midterm exam on Friday, so come over on time.